and welcome back to my channel in Economist. So today we'll be continuing with our lectures on parameter estimation, and this is going to be our final lecture on this parameter estimation topic. So we have already covered what is maximum likelihood estimation for different time series models. If you haven't watched those videos, I would recommend you to do so. I'll give the link in the description. Please check that out. And today we'll be covering the topic Yule Walker estimation method, which is also known as the method of moments. It's a very short and simple topic, so let us quickly cover that. So first understand what is Yule Walker estimation. Yule Walker estimation is also called YW estimation. So this is Yule Walker, which is also known as the method of moments. So what is the process? The process is that in this method, we equate the population moments and the sample moments to find out the parameters of the time series model. This is the short and simple definition of Yule Walker estimation. So all you need to do is to find out what is the population moments and what is the sample moments. And for that, you have to know what is the expectation, what is the variance, and what is the auto covariance function. What is the auto covariance function of the processes that we have covered till now. So this is something that you need to know before going into this estimation process. And I have covered everything in details previously. So in this video, I will not be covering how to find out the mean variance and auto covariance. If you want to know, you can check that out from my videos on individual processes that I have already covered in my playlist. So here I'll be only showing you the process of finding the estimates, right? So let us start by finding the Yule Walker estimate of MA1 process. So this is the question. You have this data available to you, y1, y2 up to yn is the sample of size n from a covariant stationary MA1 process, right? For covariant stationary MA1 process, I hope you know how to find out the mean variance and auto covariance. This is the process. This is how the process looks like. Yt is alpha plus epsilon t plus theta epsilon t minus 1, where epsilon t follows white noise 0 sigma square. So you have to find out the Yule Walker estimates for this parameter. So here you have three parameters, alpha, theta, and sigma square. So you have to find out the the Yule Walker estimates of these three parameters. So let us see how we can do that. The simple process here is to find out what is the population moment and what is the sample counterpart of it that I'll be showing. So the population moment, when we say population moment, the first thing that we do is expectation of Yt. So I hope you know what is the expectation of this. This is simply alpha. Again, if you don't know how to do this, watch that video before. So expectation. So population moment is expectation, variance, and auto covariance. So for MA1 process, the expectation of Yt is alpha. For a covariant stationary MA1 process, the second population moment is in terms of variance. Variance is what? Variance is also known as gamma naught. And this is sigma square 1 plus theta square. And we have derived all of these things, right? So variance of Yt is gamma naught, sigma square 1 plus theta square. And then you have something called gamma 1. Gamma 1 is theta sigma square. So these are the things that we know. This is the autocovariance function. And autocovariance function is existing only for gamma 1 and gamma minus 1, and that the value is theta sigma square. So see that population moments are involving the parameters alpha, alpha, theta, sigma, right? Now, in order to estimate them, we need to find out the sample counterpart of it. So sample moments or sample counterpart of population moments will be in terms of y's, because y's are known to us, y1, y2, yn. This data set is already given to us. This is how we started the question, that y1, y2, yn, these are the sample of size and this is given to us. And this is taken from this MA1 process. This is the assumption that we have made. So let's see how to write the sample moments. This is pretty simple. In sample moments, the expectation is written as y bar, right? Expectation is simply y bar. And how do you find out expectation? In statistics also, you have seen this formula. T is from 1 to n, yt. As simple as that. So take the sum of all these things and then divide it by the size of the sample, that is the value n. And that will give you your average. This is the sample counterpart of population moment of expectation, right? I hope this is clear. In population, you write expectation of Yt, but in sample, you just finding out the average in terms of y's. So y bar is 1 upon n summation p from 1 to n y. Now for variance, what you write? Variance is gamma naught cap. This cap is given whenever you are working with the sample counterpart. Please remember this. So whenever we are interested in sample values, sample counterpart, we put this cap. This cap doesn't mean the estimated value. This is simply means that we are working with the sample and not the population, right? So gamma not cap. What will this be? 1 by n minus 1 summation t from 1 to n by t minus y bar whole square. So I haven't taught you sampling distribution yet, but if you know this, then you know that 1 by n minus 1 summation t from 1 to n by t minus y bar square. This is the unbiased, estimator of variance in case of sampling distribution, not 1 upon n. In normal variance formula, we write 1 by n summation yt minus y bar whole square. But in case of sampling distribution, the 1 by n minus 1 is the unbiased and efficient estimator for the variance. So we use this formula here. And in future, I'll be, teaching you what will be sampling distribution and how we deal with that. So stay tuned for those videos. So as of now, just remember two things, that this cap here is signifying that we are working with sample and it is not implying estimation in any sense. And the second thing is that 1 by n minus 1 is here because we want to work with the unbiased and efficient estimates. And for variance, the unbiased efficient estimates will be this 1 by n minus. This is unbiased, right? To make the estimator unbiased, we are dividing it by n minus 1. More details will be given when we cover the statistics and inference, right? And the third thing, which will be the estimator for this is the sample counter, not the estimator, sample counterpart of gamma 1. This is again gamma 1 cap, right? Gamma 1 cap. What will be the formula for this? 1 by n minus 1 summation t from 1 to n minus 1 yt minus y bar by t plus h minus y bar. So this is the formula, right? I hope you understood how we calculated the population movements and the sample movements. Let me do a quick recap that in population, we find out the expectation, the variance, and the autocovariance directly from the model, right? Directly from the model. So here you have yt is alpha plus epsilon t plus epsilon t minus 1. So directly if you take expectation on both sides, you will get this will be alpha. In variance, this will be sigma square 1 plus theta square, and here it will be gamma 1. And in case of sample, we only deal with the values that are known to us. In sample, we take the sample data. Sample data is y1 to yn. So find out the expectations. Sample counterpart is average, simple average, which is y bar. For variance, it is gamma naught cap. Cap is used for sample, counterpart for the population movements. And again, you have gamma 1 cap, which is the sample counterpart for gamma 1 or the autocovariance function. Then the only task is just equate these things. So in Yule Walker, definition, I have told you that we need to equate the population movements and the sample movements. So that is what we will do. So just equate alpha with this average, equate gamma naught with this gamma naught cap, and equate gamma 1 with this gamma 1 cap. That is what we will do. So let's see. So if you equate alpha cap Yule Walker will be simply y bar, right? This is evident. Here you have alpha, and if you equate it to the sample counterpart, so alpha will be equals to y bar, which is 1 by n, which is equals to 1 by n summation t from 1 to n by t. So this is the first Yule Walker estimate, which is the Yule Walker estimate for alpha. So what we have done simply, we have this data set available to us, y1, y2, yn. So we can calculate the average, and that will give you the estimator, Yule Walker estimator for alpha cap. Now, the second thing will be to equate these two things. Equate them. So sigma square 1 plus theta square is gamma naught cap. And the third is theta sigma square is gamma 1 cap. Now, you have to find out what is sigma, what is theta. So for that, what you can do, you can divide this by this. So sigma square 1 plus theta square upon theta sigma square. This is gamma naught cap upon gamma 1 cap, right? So this will cancel out. So 1 plus theta square upon theta. This will be this gamma naught cap, gamma 1 cap. Now please understand that this gamma naught cap and gamma 1 cap is, you know, we can find this out explicitly because we have these YT values available to us. So we can explicitly find out what is gamma naught cap and what is gamma 1 cap. So this value is a constant. Suppose A. Some value, this will be some value which is known to us. Suppose this is A. So this will be a quadratic in theta, right? This is a quadratic in theta. So you can write it as 1 plus theta square equals to A theta, or theta square minus A theta, theta square minus A theta plus 1 equals to 0. So this is a quadratic function, right? This is a quadratic function. And when you will solve this, you will have two values of theta. Two values of theta, right? Quadratic, whenever you solve a quadratic equation, you have two values of theta. Now the question is which value you will take. The answer to this question is any value. For any value of theta which satisfies this equation will represent the Yule Walker estimation of sigma square, right? So let me write it. For any theta, the solution is valid, right? For any theta, this solution is valid. And once you know this theta, so you know this, then use this equation. So you have theta sigma square is basically gamma 1 cap. Once you know the Yule Walker estimation of theta, so what will be sigma square cap Yule Walker? Simply gamma 1 cap by theta cap. So once you, since you have two values of theta cap, so sigma cap values will also be 2. And that doesn't matter, any value will do. So this is how you find out, this is the process of finding out the Yule Walker estimate for MA1 process. So you start with the model, you find out the population moments, you find out the sample moments, you simply equate them to find out the estimators. And similar thing we can do for the ARP process as well. This is the general form of ARP process. Let us quickly do the population moments. So what will be the expectation? Expectation is alpha upon 1 minus summation I from 1 to P phi I. This is the expectation. We have derived it. Gamma naught is basically variance of phi t. This is phi 1 gamma 1 plus phi 2 gamma 2 all the way phi p gamma p plus sigma square. And what will be the autocovariance function? Autocovariance function is phi 1 gamma h minus 1 plus phi 2 gamma h minus 2 plus phi p gamma h minus p, and this will be true for h greater equals to 1. So these are the population moments. Now what you can do, you can use this autocovariance function and vary the value of h. So for h equals to 1, this will be the value. For h equals to 2, this will be the value. And for h equals to p in general, this will be the value. Now once you have that, what you can do, you can write it in a matrix form. You can convert this entire thing, this entire expression in a matrix form that I have already done for you. This is the matrix. So please see here. This is the vector gamma 1, gamma 2, gamma p, and this is on the left hand side here. So in general, what we can do, we can write this particular vector as gamma curl, right? This particular vector is gamma curl, and then you have this big matrix. This is composed of these gamma terms, gamma. Everything gamma is the next term. So here you have this thing. So let me write that with this symbol. This represents this entire matrix. And then you have all the phi's, phi 1, phi 2 up till phi p. And this is given by this vector. Let me call it as phi curl. Right? In vector, when we write vector, we use this curl sign. So let me write that this gamma will be nothing but gamma 1, gamma 2 up to gamma p. And what will be this phi? Phi is basically phi 1, phi 2 up to phi p. As simple as that. So what we have done just convert this thing into a matrix form, right? This will make our calculations easier. Okay. Now the next thing is to calculate the sample moments. Again, y bar is the same. Y bar is the first sample moment that we can calculate, t from 1 to n by t. This is the same as before. Then we have variance. Variance is also the same. Variance is written as gamma naught cap y 1 upon n minus 1 again for making the estimator unbiased. So this will be yt minus y bar whole square. And the third is gamma h cap. This is a little different. 1 by n minus h. Summation t from 1 to n minus h. This will be yt minus y bar and yt plus h minus y. So these are the sample moments for ARP. Right? Now we have to equate everything. So if you equate the population moments with sample moments, what we can see is that phi curl cap can be found out this, let us start with this gamma curl. Okay, let me write gamma curl. We have written this to be this into phi curl. This is what we have. So what we can write about phi curl. Phi curl cap Yule Walker can be written as this matrix inverse times gamma curl cap, right? This will be inverse. This will be going in this side, and we will assume that this is a non-singular matrix. This is a non-singular matrix. Non-singular matrix, and hence it is invertible, right? So in ARP process, we want to find out. See here, these are so this is the phi curl cap portion. Will give you Yule Walker estimates of this phi's, right? This Yule Walker estimates of phi's will be found out using this thing. Then we have to find out what will be for alpha and what is for sigma square. So let's see. You have this expression. Once you equate that, you can find out taking the inverse, you can find out what will be phi cap Yule Walker estimates, where gamma curl cap will be the Yule Walker estimates for each of them. Yule Walker estimates for each of them. And then for the inverse cap, sorry, here you will have also have cap. Here you will also have cap, and this will be the cap of individual expressions. Since we are working with the general form, the expression looks like this. Once you have the data set available to you, this will be reduced to small numbers, right? So what we have done, we have used this matrix notation that we have derived, and we wanted to find out what will be gamma cap Yule Walker estimate. So I have taken this on the left hand side using inverse, and then if you equate it with the sample, you will have this expression. So simply this, and gamma curl cap will be the estimates of individually all the gammas, and here this matrix inverse cap will be something like this. And the final thing that we wanted to show is the what will be alpha and what will be sigma. Since phi's are already done, right? This is the expression for phi. The rest two, estimates are, the parameters are alpha and sigma. So we have equated the population and the sample moment. Y bar is expectation of yt. Expectation yt expression is this. So you can simply multiply. So alpha will be this multiplied by this entire thing. So we have done that, and this will be the, not MLE, sorry. This will be the Yule Walker estimate of alpha cap. You can do it on your own. The steps are given to you. And here also you will have Yule Walker. And this thing is done using the variance formula. So variance, I have equated the variance. So this This is the variance, and if you take this entire thing to the left hand side, you will have gamma naught minus. This is gamma curl transpose. Gamma curl transpose. Transpose is for this. This is, you have to multiply gamma with 5. So see, gamma is gamma curl. This is the gamma curl expression. This is what you have, p number of rows and one column. So it is p cross 1. This is p cross 1. So when you take transpose, it will be 1 cross p. And then you have phi's. So phi's will be, phi is also p cross 1. So phi is p cross 1. So when you multiply this, this will be 1 cross 1. This will be a singular term, right? This will be a singular term. And here you have gamma naught. So once you estimate that, estimated value will be gamma naught cap minus this cap into this cap. So I hope you got the process. You can, pause the video, take a screenshot and do it on your own. You will get the process. I hope you find this understandable. So I have equated the population and the sample movements, nothing else. The process is the same. This is the population movement. I have converted it into a matrix form just for simplification of our process. Once you have data, you can see it's very simple. Then you have the sample movements, just equate them to get the Yule Walker estimate. So this is the Yule Walker estimate for phi, this is the Yule Walker estimate for alpha, and this is the Yule Walker estimate for sigma square, right? And that is all for the ARP process. And if you know the general form of ARP, you can find out the Yule Walker estimate for any of the AR processes. And finally, I have given you some homeworks. I have derived what will be for Yule Walker estimate for MA1. So please do this for MA2 process. Again, the same thing. I have already talked about what will be the mean variance and autocovariance for MA2. So use that knowledge to find this out. AR1, I have derived AR for ARP. So do it for AR1 and for AR2 as well, right? So that is all about the parameter estimation of time series process. And by this, we have ended our chapter of parameter estimation. I hope you like this video, and if you do, please give me a thumbs up and please subscribe to this channel, A Economist, for further videos. And in the next session, I'll be going into the test for stationarity, and I'll be covering what is the Dickey-Fuller test and the augmented Dickey-Fuller test. And that is going to be our final lecture for the time series playlist. So thank you for joining in, and I hope you like this video, and thank you for your time.